Hi everyone, Assalamualaikum. In the previous video, we have discussed applications of first order ODE, alright? And we discussed application of separable differential equation, which is population growth and bacterial colony, radioactive decay, and Newton's law of cooling, alright? So in this video, we will discuss the application of linear differential equation, which is mixing problems. Alright. Alright, now we look at mixing problem using linear equation. To solve mixing problem using linear equation, we can use this formula. dq over dt plus r2 over v naught plus r1 minus r2t q equals to b r1. Okay, where q equals to the amount of substance in kg, okay, or other equivalent units, okay. B equals to brine solution measured in kg per liter or other equivalent units, okay. T equals to time measured in second, minutes or hours. V naught equals to initial volume of chemical measured in liter or other equivalent units. R1 equals to rate in measured in liter per minute or other equivalent units. And R2 equals to rate out measured in liter per minute or other equivalent units. Alright. Alright, if brine solution B is not given, then we can assume B equals to 0. Alright. And after we integrate, we can find C. Okay. And to find C, we substitute T equals to 0, Q equals to initial Q, okay, or initial amount of substance, okay, which denoted by Q naught, okay, into the equation. Or if Q naught is not given, we can assume when T equals to 0, so Q also equals to 0. Alright. And when we use this formula, okay, R1 or rate in can be equals to rate out, or R2 or rate in not equals to rate out. Okay. For rate in equals to rate out, okay, it can solve using separable or linear differential equation. Alright. And for rate in not equals to rate out, we can solve using linear differential equation only. Alright. So the mixing problem can be solved using separable or linear differential equation. But the separable equation can only use when the rate in is equals to rate out. Okay. While linear differential equation can be used for both rate in equals to rate out or rate in not equals to rate out. Alright. So to avoid confuse, we will discuss the mixing problem using linear differential equation, since it can be used when the rate in equals to rate out and the rate in not equals to rate out. Alright. Alright, now we continue with example 7 under mixing problem. A tank contains 1000 liters of brine with 15 kg of dissolved salt. Pure water enters the tank at a rate of 10 liters per minute. The solution is kept thoroughly mixed and drains from the tank at the same rate. How much salt is in the tank after 40 minutes? Alright. Okay, first, we extract the given information and write into the symbol below. Okay, we write symbol V naught B R1, R2, time, and Q, right? Okay, and then we write an appropriate unit for each symbol. Okay, for V naught, we write unit L. For B, we write unit kg over L, liter. For R1, we write unit liter per min, and same goes to R2. And for Q amount, we write unit kg. Okay, then we can extract one by one. Okay, from 1000 liter here, from the unit liter here, we can put here. Okay, V naught equals to 1000 liter. Okay, and then from 15 kg here, okay, the unit is kg, so we can put here Q equals to 15 kg when T equals to 0, initial T, okay. And then from 10 liter per min, from unit liter per min here, okay, we can write R1 and R2. And then from the word enters here, okay, means it is the value for rate in, okay, which is R1. So we can put 10 here, okay. And then from the word same rate, okay, means R2 also equals to 10 liter per min, okay. And then how much, okay, means Q equals to question mark. After 40 minutes means time equals to 40 minutes, okay. So we extract all the value and put into this box. Alright. Alright. In this example, after we put a value for each variable, okay, it is found that there is no value for B here. This means that B is not given. Alright. Okay, so when B is not given, so we can assume B equals to 0. So we put 0 here. Alright. Then we can substitute V naught, B, R1, and R2, okay, into this formula. Alright. Okay, so we can continue with step 2 under linear equation. Okay. Alright, we substitute V naught, B, R1, and R2 into this equation. dq over dt plus R2 over V naught plus R1 minus R2t Q equals to B R1. Okay, we substitute V naught here, and then B here, R1 here, and here, and then R2 here, and here. Alright. No need to substitute dq dt, t and q. Okay, we just substitute these 4 items only. Alright. Okay, and after that, we have dq over dt plus R2. We replace by 10 here over V naught. V naught we replace by 1000 here plus R1 equals to 10 minus R2 also equals to 10, and then T, Q, and then B equals to 0. B is not given actually, so we assume equals to 0, and then R1 equals to 10. Alright, then we can simplify. 10 minus 10 equals to 0, so 0 times T equals to 0, and 0 times 10 also equals to 0. Okay, so we can write dq over dt equals to 10 over 1000 q equals to 0. Okay, and then dq over dt plus 10 over 1000 equals to 0.01 q. Okay, equals to 0. Right? Alright, from the previous slide, we get dq over dt plus 0.01 q equals to 0. Okay, from step 2. Okay, so this equation is similar to linear equation dy over dx plus pxy equals to qx. Okay, where variable y here means q. Okay, dt here means dx. Okay, and 0.01 here means px, and 0 here means qx. Okay, and then from linear equation, after we find dy over dx plus pxy equals to qx, we need to find integrating factor if, which is equals to e to the power of integration of px dx. Right? So to solve this linear equation for mixing problem, okay, we need to find the integrating factor if. Right? So if here equals to e to the power of 0.01 dt. Okay, px here means 0.01. Okay, from here. Right? And dx here, okay, means dt. Okay, right. So 0.01 here from 0.01 q here. Okay, from here. Right? So we integrate e to the power of integration of 0.01 and then dt. Right? And then we get e to the power of integrate constant. We get constant and then t because we integrate with respect to t. Okay? Alright, no need to put plus c here. Okay? And then we need to find q. Okay, q is the amount of salt, okay, in terms of time and constant c. Okay, so to find q, okay, we can refer from linear equation y times if equals to integration of qx times if dx. Okay, so we can write q times if equals to integration of 0 times if dt. Okay, qx here, okay, means 0. Okay, so qx here, so we replace by 0 here. Okay, and then dx is dt. Okay, from here also dx equals to dt. Okay, y equals to q. Okay, from here y equals to q. Alright, so that's why we get q times if equals to integration of 0 if dt. Okay, then we replace if equals to e to the power of 0.01 t. Okay, then we get this. Okay, and after that we can write q times e to the power of 0.01 t equals to 0 times any value equals to 0. So we get integration of 0 dt. Okay, then to integrate 0 with respect to t, okay, we can refer from derivative. When we differentiate constant, okay, it becomes 0. And when we move derivatives to the right hand side, we can get integration. Means that we can get integration of 0 dx equals to constant. Okay, so now we have right hand side is integration of 0 dt. So we will get c constant here. Okay, for left hand side, we don't need to integrate because there is no integration sign here. Okay, so we get q e to the power of 0.01 t equals to c. Alright, then we can write q as a subject. Okay, because in step 4, we want to find q. Okay, in terms of t and c. So from here, we write q as a subject. So we can move times e to the power of 0.01 t to right hand side. So we get c over e to the power of 0.01 t. Right? Then from properties of indices, we can move denominator to numerator. And when we move denominator to numerator, the exponent should be negative. Okay, Alright, so we get this. Q equals to C e to the power of negative 0.01t. Okay. So now we find Q in terms of T and C. Then we write as equation 1. Okay, to solve the next question. Alright. Alright, from the previous slide, under step 4, we get Q equals to C e to the power of negative 0.01t, and we're naming it as equation 1. Okay, so we can continue with step 5. Okay, substitute T equals to 0, Q equals to 15 kg into equation 1 to find C. Okay, from the previous slide, okay, we extract the information from the given question and we get T equals to 0, Q equals to 15 kg here. Okay, so from here we can substitute into equation 1 here to find the value of C. So from equation 1, we replace T equals to 0 and we replace Q equals to 15 kg. Okay, then we get 15 equals to C e to the power of 0 and e the power of 0 equals to 1. Okay, so we get C equals to 15. And after that, we substitute back the value of C into equation 1 here. Okay, alright. So we will get the amount of salt at any time t, okay, equals to Q, okay, equals to 15 e to the power of negative 0.01 t. Alright, 15 here comes from C here, okay, the value of C here. Okay, and then we naming it as equation 2. Okay, alright. So now we want to find the amount of salt after 40 minutes. Okay, so we can substitute T equals to 40 minutes, okay, into equation 2 to find Q. Alright, so from equation 2, okay, we have Q equals to 15 e to the power of negative 0.01 t. Okay, so now we replace T by 40. Then using calculator, we get Q equals to 10.05. Okay, then we need to put unit here. Okay, so from the given question, Q is given in kg. Okay, so we can write Q equals to 10.05 kg here. Okay, so this is the amount of salt after 40 minutes. Okay, we replace T equals to 40 into equation 2 here. Alright. Coming up next, mixing problem, rate in not equals to rate out under application of linear differential equation. Thank you for watching. Stay tuned. Bye. Assalamualaikum.